Welcome back to the Distributed Control and Automation Framework video series. In this video, we're going to take a peek under the hood of how the DCAF engine actually works. Buckle up. Let's take a look at the example project that ships with DCAF that we've looked at in several of the other videos in this series. If you open up your example finder, search DCAF, open the temperature controller example, you'll find host main VI. In all of our other examples, we've simply taken a look at this at the surface level and hit run. Let's dive down a little deeper and see what this is actually doing. Here, we're going to be looking at the configuration file and looking at the particular target as specified here and launching the different engines required. Let's take a look. So, loading in the file, loading in the target, determining how many engines we've got and what configurations there are. Then over here is where we're actually opening and initializing the engines themselves. Here again, we're launching the engines. Now here's where they first hit a dynamic dispatch window. The engines that we ship with DCAF are themselves plug-in based. It is possible to override the engine and provide your own engine implementation if you so choose. I don't recommend it since we've put in quite a lot of work to make our standard engine as efficient as we possibly can. But the possibility exists if you wish. Within the standard engine, we've got quite a bit of code to set up everything in terms of the communication pathways into the engine, as well as asynchronously launching an instance of the standard engine VI. If we launch this, take a look inside here. This is what's actually running when you launch a DCAF engine. Out here is a state machine determining where we are in the state machine. Are we waiting to get a configuration? Are we in a safe state? Are we getting set to run? Or are we in the run case, in which this case is called timed loop? The reason it's called timed loop is pretty clear once we take a look inside our primary control loop. So get in here, a little bit hard to see on the screen because there's quite a bit going on. This is a very heavily optimized time structure that's going to run at whatever period you select within your system. Now, because the core functionality of DCAF exists inside one of these time structures, everything in here is actually going to run single-threaded by default. That's both a major performance improvement in the sense that we don't have to do any thread swapping or context switching to do our executions. It also means that we're limiting as much as possible any memory copies or any other jitter that can be introduced into the system. Now, we also specify in a sequential order what operations happen in the system. And those operations are the input, process, and output methods that get defined on a per module basis. You may recall from our documentation, other videos, or live in-person sessions that the way that DCAF works is by taking tag-based single-point data with a single writer and making that data available in between different modules. If we take a look at the core of the engine here, this pink wire that connects the input, processing, and output methods is the core of DCAF. That is the tag bus. That is the bus that actually carries the tag data itself. And it's got quite a bit on it, as you might imagine. So I'm not going to go into the full details there. But what this provides is this wire is the global repository within this engine of all tag data to be passed between modules. Each module, it basically registers for a smaller subset of the overall available data. If we look at a processing module, you might notice these functions. This is basically taking the full set of data on the engine's tag bus, pulling out the individually registered pieces of data that this particular module needs, and passes it to the module. Since this is a processing module, it takes both data in and provides data out. So we take the few smaller subset of tags that this module produces and merge them in with the larger data table here that lives on this wire. It is a by value transfer of data. This is not a reference-based system. This is not a pointer. This is actual data on the wire, which takes advantage of one of LabVIEW's greatest strengths, which is its data flow system and all the compiler optimizations over the last 30 years that make that kind of data transfer very efficient. Also, because we put all of the data on the wire, if we instantiate more than one engine, the data space is actually scoped just to that engine because the data is only on this wire. We don't make this data global. It is not exposed out to the rest of the system unless you have specifically decided that you want to expose it as part of your configuration. For example, allowing the CVT module to read the state of data. If we look at, say, the input action, this is a big for loop for each module defined in the system, assuming that it actually has an input method. Call the input method. Here we get to another dynamic dispatch layer where each module in its runtime class, if it defines an input, will have an override method here. Typically, any modules that you have that are reading values in from hardware and putting them on the bus, these will have an input module defined. So for example, the UI reference module, the one that communicates to data items on a front panel, this is how it actually works under the hood. We're getting control values by index for each of the different data types that exist on that particular front panel. And then all we do is put each data type, a collection of data items for each data type, into the data table of the appropriate data type, at which point it's on the tag bus and can be referenced by later modules on a read basis. And if you notice back at the time structure here, we guarantee that all input methods are called, then all processing methods, and then all output methods. Because we're in a single-threaded execution, it's very easy for us to guarantee this, then this, then this. Now, if what you require in your system is some more asynchronous operation, for example, you have a processing method that only needs to run every now and then, maybe once every 10 iterations of the main control loop, but it takes a long time to run, for example. One of the other options that you have is to call a module asynchronously. So there's a little switch in here for sync, async. Synchronous, as be one at a time, wait for the module to finish, put its values out, go to the next module, wait for that one to finish, go to the next module, wait for that one to finish. Asynchronous, it actually will break out the execution of that particular module into a separate free-running thread on the system. We provide all of the communication pathways to and from that module, and you don't even have to change or adjust your module. All that you'll need to do to take advantage of that particular feature is on any individual module that you wish to enable it on, click the checkbox for asynchronous on that module's properties in the engine configuration on your configuration editor. You don't have to change your module. You don't have to make any adjustments to your mappings. All you have to do is click that button, and we'll take care of setting up the queues, in this case RT-FIFOs, to handle all the communication to and from the module and you don't have to do a thing. It's already as optimized as we can make it in terms of the data transfer speed as well as memory performance. So, the major advantages of the framework is that you don't have to worry about all this low-level plumbing code, since we have already done all of that for you. Now, a few other things to keep in mind with the engine. Another feature that's a little bit interesting to take a look at is how I manage timing in DCAF. You may have noticed that the core of the engine is a timed sequence structure, as opposed to a timed loop. That's because we want to let you choose what your timing source is going to be. In the configuration, you have the ability to select a timing source. And what we do inside the system is we wait on that particular clock to iterate. And of course, we have the ability to choose how many ticks of that clock we're going to wait for. We provide a timing API already built into the system to wait on any of the different timing sources you might have. So here's another dynamic dispatch window. We can go wait off of microsecond timing, the scan engine sampling clock, or a millisecond timing. If there are any future developments in the timing space, which is under active R&D development right now, we'll be able to plug in an additional one in here once that becomes available, without any changes to your code whatsoever. Again, a nice benefit of having the framework in place to handle all this details that every application should have, but not every application actually has. Hopefully that gave you a little bit of insight into how the engine actually works. If you discover that you have more questions, please take a look at ni.com/DCAF. We have a community of users and developers who are actively patrolling those forums. Please send us a message there, make a post, ask. We'll be happy to help. And of course, if you find that there's contributions that you wish to make to the system, or a bug that you think that you can help fix, come visit us at github.com/LabVIEW-DCAF and become a contributor to the framework yourself. Everything that's in the framework now is because of either user feedback from our customers or direct contributions from our customers themselves into the framework. We hope to hear from you soon.